So today we're getting into, we're going to do a little bit more with the exponential graphs. Today we're going to get into a little bit of story problem work. So this is 7-1 continued. I do want to, it's not going to take long, we're just going to kind of introduce some formulas. If we put down yesterday this equation where we had a and then b raised to the power of x minus h and then plus k. So this was our generic formula for graphing, correct? Where h does what? Moves it left and right. K does what? Up and down. And a does compress, right? Or stretch. And then if a is negative, it gets flipped or reflected, right? So now let's talk a little bit about what b is and what a difference that makes. So if b is greater than 1, if b is greater than 1, then this is called exponential growth. And my graph look like this. However, if b is greater than 0 but less than 1, then it is called exponential decay. And that graph looks like this. It's flipped.
I don't know why. It sounds like a really weird name.
Exponential decay?
Yeah.
Could be a fun band name, I guess.
Oh gosh.
Exponential decay.
In my garage band. When you're trying to be edgy but you like math too.
Alright, so I just kind of wanted to put those two words out there. We are going to be dealing with growth and decay. You're going to get two different problems today. One dealing with growth, one dealing with decay. But we're going to be using a couple of specific variations of our exponential formula. So we will be using the following formulas. A of t equal to a times 1 plus r raised to the power of t. Or we will use a of t equal to a times 1 minus r raised to the power of t. We'll use one of those two formulas. What's the difference between the two? One's plus and one's minus, right? Which one's growth? I heard both. No. The top is growth.
Oh my gosh.
No, the top is growth, right? You alright? Okay. Which makes the bottom one the decay. Now in both formulas, the A, the R, and the T all represent the same thing. So A represents the initial amount. The amount that you start with, right? And then R represents, what do you think? Not the ratio, the rate at which it's growing or decay, right? So it's the rate. Now rate is typically given as a percent. It's usually given as a percent. But if you're going to use it in your problem, it will be a decimal. It has to go in as the decimal. You cannot put a percent into a problem. A percent is not a number, right? And so you have to change it to its decimal form. And then t, of course, represents the time. Okay. T is time. Now, you're going to get two problems today. One growth, one decay. Your job will be to figure out what goes where and then answer the questions they ask. Make sure you actually read the problem. Okay? Had lots of interesting conversations with last period. Read the problems. Okay? Yes?
So in the equation, that's 1 plus r and 1 minus 1?
Mm-hmm. Yep. If it's growing, we're going to add the rate. If it's decaying, we're going to subtract the rate. Okay. So, that homework is on page 455 again. And I'm going to ask that you do numbers 7 and 12.
Thank you.
7 and 12. So we'll get to that in a minute. We're not done. So, I would also like to start today, chapter 7, section 2.
What?
I know, right? So, chapter 7, section 2. Oh. So, 7.2 is solving exponential equations. Okay, now, on occasion in math, we write down statements and make sure that we understand them, and sometimes they seem like they should be rather obvious. But then their applications can be quite interesting. So today, we are writing down this obvious statement: b raised to the power of x equal to b raised to the power of y. If that is true, if we have that statement, what do we know about x and y?
They're the same.
They're the same. So if b raised to the power of x is equal to b raised to the power of y, then x is equal to y.
10. I wrote 10 instead of 10. Good job.
Does that make sense? Are we good with that statement?
Yes.
For example, if I have 5 raised to the power of x, and that's equal to 5 raised to the power of 3, then
X equals 3.
x equals 3.
Wow.
I know, right? Okay,
So difficult.
now let's make things slightly more complicated
Oh no, I should
and write 5 raised to the power of x equals 125.
Oh, that's not that bad. I think it's fine.
What's the square root of 120?
X still equals 3.
Oh,
Now, how do we know that?
Because 5 cubed.
Because 125 is the same as 5 cubed. So what I can do, now, of course, we have other ways of playing with this, but what we can do is, of course, rewrite the 125 as 5 cubed, which we can then figure out that x is equal to 3. Does that make sense so far? Are we good?
yes. See.
Okay.
Indeed. Ow.
So let's make things slightly more interesting. Let's say we have 2 raised to the power of x. And that's equal to 8 raised to the power of 3. What do we got? What's x? X is not 3. And the reason that it's not 3 is why? Why is it not 3?
It's gonna be 7.
Yeah.
Oh, yeah, B is.
It's not the variable. Yeah. Because b isn't the same. And b would be the base. The bases are not the same, right? 2 and 8 are not the same. Now, my last class suggested that I multiply one side by 4, that would make it an 8, and then we could just set the x equal to 3 and we'd be good, right? No! No! Right? We can't do that. Now there are a couple... Right. There are a couple of reasons why we can't do that. One of them... Well, 4 does exist, but one of them is the fact that if you do something to one side, you have to do it to the other side. So otherwise you're not maintaining the equality of your statement, right? So if you multiply this side by 4, you have to multiply this side by 4, and I still don't have a way to make that work. Now, the other reason that this doesn't work is if you multiply this side by 4, does this become an 8? No. No. Okay? So for those of you that were like, well, yeah, 2 times 4 is 8. That's true. But this is not a 2. This is 2 to the power of x. Right? And the order of operations, which still exists, right? Just because we're not in elementary school and middle school, doesn't mean the order of operations doesn't exist. The order of operations says that you have to deal with exponents before you deal with multiplication. Okay? So you can't multiply the 4 times the 2 until you deal with the x, which we can't do. So it would remain a 4 and then 2 to the x, and it's not very helpful. Okay? So that does not work. Now, I did hear someone in the audience say that x is equal to 9, which, by the way, is correct. Why?
Because 2 cubed and then you...
8 is the same as 2 to the 3rd power, which means we can do this. We can rewrite 8 as 2 to the 3rd power. And then, because the 8 was being raised to the 3rd power, then 2 to the 3rd is being raised to the 3rd power. And when you have a power raised to a power, we multiply the exponents together. And so we have 2 to the power of x equals 2 to the power of 9, which means that x is equal to 9.
Wow.
Does that make sense?
Yeah.
We good? All right, let's try one more. Uno más. Okay. Let's go with 9 raised to the 2x minus 1 power equal to 3 raised to the power of 6x.
Yucky. Whoa.
No, you shouldn't need your calculator for this.
Big yucky.
Yeah, Ty's gosh.
What do? What needs to happen here?
I wish I knew.
Yeah.
Wouldn't you just add 1 to the 6x plus 1?
What?
Second side?
No, I can't.
Because the left side is 3 to the 6x minus 1.
That's 2.
That's 2.
No, okay, well, I did the 3 squared and then, oh wait, no, it's 4x minus 1. Never mind.
Okay. Yes.
Can you put like 6x plus 2 on the right side?
Just add a 2 over here.
No. Yeah.
Like your like the exponents, it's like
No.
or is that not how you do it?
Whatever you do to one side, you have to do to the other side. So, going in and sort of just adding something to one side is never really going to work with an equation, because you're going to immediately turn around and do the same thing to the other side, and whatever you were trying to balance is now the other side's. Do you see what I'm saying? So you can't quite work it that way.
The other side gets
Right?
the same bump.
We have to find a way to rewrite so the equality is maintained, but it looks different. And remember what we've been playing with here, right? We started with this first statement where I had the 5 to the power of x equals 5 to the power of 3. And then we came down here and we had 5 to the power of x equals 125, and we had to change the 125. Then we had 2 to the power of x and 8 to the power of 3, and we had to change the 8. The whole point of what we've been working on is getting the bases to be the same. This only works if your bases are the same. So what do I need to do? Yeah, we're going to change it to 3 squared.
And then you have to take 3 squared and multiply it, well, raise it to 2x minus the power, which means you multiply x minus.
Oops, that's not a 6, that's a 3. So,
That is not what you were.
That's why I said add the 2 because you have to like square it.
Is that?
but adding a 2 is not the same as adding a 2 is not the same as squaring.
I think he meant like putting the 2 there, like when you add potatoes to like potato salad. Like,
Okay, let's just stop there. Because adding potatoes to potato salad is... Okay, alright. So, do we see how we got the 3 squared? Right, is everybody copacetic with that? Alright. Now, what happens when I raise a power to a power?
You multiply.
We multiply. Which means I'm going to take the 2 and I'm going to distribute it through 2x minus 1.
Distribution.
And so we wind up with 3 raised to the 4x minus 2 power equals 3 to the 6x power.
Good job.
Yes, Caitlin.
Okay, so I don't know if this works, but like, if you did, so the right side, if it's 6x, and then you did minus 3, and then the thingy, and pulled out a 2, no, a 3.
Um,
Can you do that?
no. Because you're doing it to one side. If you just subtract a 3 on that side, you have to subtract a 3 on the other side, and now you've kind of canceled out what you were trying to do. Because now I have the same problem on the other side where there's something different. You see what I'm saying? Okay? So you're not going to be able to just look at something and go, oh, I just need to add this. Because then you have to turn around and add it to the other side, and now you've sort of negated what you were trying to do. Okay? All right. Now, however, my bases are the same. Correct? What do you got, Justin?
So would you just take what you have in the exponents of each side of the equation and then make it into like a different equation and solve
Yep. Now, I have 4x minus 2 equals 6x.
Whoa.
And we just have a little equation to solve, right? Subtract the 4x from both sides. I get negative 2 equals 2x, which means that x is equal to negative, sorry, let's try that again. Negative 1.
My God.
I mean, you were close. All right. So, are we good? That's what you're doing today. Your homework is on page 464, and you're going to do numbers 1 through 5.
Uh-oh.
All right, get busy.